Okay, so I'm just starting a fresh recording again. So again, we discussed vectors in the last class. We looked at some examples. Now we're looking at an application similar to one of your homework problems. And don't forget, example 7 in the textbook has also a nice example of an application in section 9.2. So in this problem, we have ropes of different lengths that are fastened to a decoration suspended over a town square. The decoration has a mass of 5 kilograms. The ropes are fastened at different heights. Make angles of 52 degrees and 40 degrees with the horizontal. Find the tension in each wire and the magnitude of the tension. Okay, so all right, are there any questions so far with this? All right, let's go. How should this problem be started, do you think? How do you think this problem should be started? What would be helpful? Definitely, Robin. We need to have a sketch. We need to have a sketch of this problem. And actually, let me go to the next page. I have a sketch, but my sketch is not quite right because, well, yes, that's right, Eric, a force or a tension diagram. So I'm going to have to adjust my sketch a little bit here. I'm going to have to adjust it, but that's okay. I can do that. I can do that. So the heights are supposed to be different, and I drew it where the heights were the same. So I got to correct that in the picture here. So let me go ahead and do that. I can do that. Okay, so there we go. Just have to clean this up a little bit. Just have to clean it up a little bit. Easy enough to do. If I were in the classroom, I'd be doing the same thing that you're seeing now. A little more challenging, of course, because we're doing remote learning. Okay, the 40 degrees is here. Okay. All right, so okay, that looks fine. Okay, and you're copying the picture down, so it's taking you a little time to get it down, but that's fine. Okay, so we have the holiday, the decoration is right here. I get this thing off. Okay, the decoration's right here, and it weighs 5 kilograms. And you have these two ropes or cables, cable here and a cable there, that are connected to like bolted into the wall, bolted into the. I have to be. I mean, I want to be careful how I phrase it, but they're connected to these two platforms at different heights. Okay, and the angle here. The angle here is 52 degrees that the tension wire makes with the platform. And the other tension wire, the one that's 5 meters in length, that's why I call this tension vector T5. The other tension vector is T3. So it corresponds to ropes of 3 meters and 5 meters in length. And that's why the heights are different. That's why the heights are different. Although you don't, you could just have the I mean, it's fine. I mean, it makes sense. It makes sense. So these ropes are holding up the decoration, and we want to find the tension in each wire and the magnitude of the tension. And believe it or not, we have enough information to answer the question. So first of all, what we have to do is rely on trigonometry here. So if we look at the first platform here, okay, the tension, the 3 meter rope is at an angle of 52 degrees with that horizontal platform. Well, that means by alternate interior angles, if you remember that from geometry, this angle here has to be 52 degrees as well. So what I'm going to do is I'm going to say the cosine, well, by right triangle trigonometry, the cosine of 52 degrees has to equal the adjacent over the hypotenuse. Well, the adjacent side in the diagram is x, but that x is negative, right? That x is negative because if we think of the Christmas decoration as being at the origin, okay, this x is negative, and so I put negative x there, so that I have positive sides. In other words, I have this right triangle here on the left, and I want to have my leg and my hypotenuse positive. Well, that means the leg has to be negative x, and the hypotenuse would be the magnitude of the tension of the 3 meter rope. Okay? Now on the other side, we have not the cosine of 52 degrees. Hold on here. I knew I would screw that up. I'm going to be getting one of these I mean, I'm okay with the mouse, but I think I'm going to be getting one of these stylus pens pretty soon. But the cosine, I'm sorry, not the cosine. Oh man, well, hold on. The sine of 52 degrees is equal to y over the magnitude of t over 3. Similarly, well, first, are we okay with these two problems? Are we okay with that? Let me know if you have any questions. Okay, good. Thank you. Thank you. Just trying now. I got to fix this thing again. There's the other tension vector. And it's off of that platform there. Okay, so the tension for the 3-meter rope, the tension for the 3-meter rope is going to be X times I plus Y times J. Okay, and the X, by virtue of this first equation, X has to be equal to negative magnitude of the third of the tension 3, tension T sub 3 times the cosine of 52 degrees. Similarly, since the sine of 52 degrees is y over the magnitude of the tension T sub 3, we would have then the component, the J component, would be the magnitude of the third tension times the sine of 52 degrees. Let's see, Christopher's asking, are you using X as a measure of tension in the X direction or a distance? The X and Y are components of the tension T sub 3. They're component forces. That's correct. They are component forces. And so the signs matter. Okay. Okay. And if we then look at this, that's your 40 degrees there now. Okay, and so you can write the fifth tension vector similarly as you did the third tension vector. I should say that the T sub 3 tension vector, the T sub 5 tension vector, which is the tension vector corresponding to the 5-meter rope, that can be written similarly as you wrote the T sub 3 tension vector for the 3-meter rope. Okay, and you would have trigonometric. You would have trigonometric equations for the cosine of 40 degrees and the sine of 40 degrees over here for that other right triangle. And this would get you this result. So far, are we good? Are there any questions? Are there any questions so far? Please let me know. All right. Well, so what we have to do naturally is we have to solve for these tension vectors. But we note that if we were to add up the weight vector for the holiday decoration and the two tension vectors, well, the system is in equilibrium. The holiday decoration is not, it's stable. It's stable. So that means the sum of the two tension vectors has to equal the negative of the weight vector. Because see, the weight vector in the picture The weight vector in the picture is pointing down, right? But the tension vectors are pulling up. So the pulling up of the sum of the two tension vectors has to equal the negative of the weight vector. And that's how we get this here. Is this okay, what I wrote here? Is that all right?
I have one question.
Yes, Ron.
So wouldn't that only be true for the y components of both forces? Of both tensions?
True. Well, it's true for the x components will have to cancel each other out on those two. I want to phrase this. I want to phrase this the right way. Hold on. The x components for your tension vectors, the sum of them are going to have to equal 0 because, like you say, the holiday decoration is not like there's no force moving it to the left or the right. It's just down, right? The weight is pulling it down. But nevertheless, I want to phrase it. Let's phrase it the right. Let me phrase it this way. How many variables are there in this equation that we have to solve for? How many variables are there in this equation?
There are two.
There are two, and that means we need two pieces of information. Now, let me ask you this. Are you comfortable with this statement here? I mean, are you comfortable that, of course, the weight is of the holiday, or the mass of the holiday decoration is 5 kilograms, but then the weight due to gravity is 9.8 meters per second squared. And so tension T3 plus tension T5 equals negative the weight vector, and that's going to have to equal 49J. Are you okay with that? Because the reason I'm asking is this equation here, this vector equation, saying that T3 plus T5 equals 49 is, if you understand that, we can get to the next step. And it'll answer your question regarding those component forces.
Oh, I get it.
And that's right. What Eric's saying in the exactly right. What he's saying in the chat window.
I was just looking at the tension as a scalar rather than a vector itself.
Yeah. You have to think of it as vectors. You have to start off with the vectors. All right. So you're okay with this equation here? You're okay with
yes.
that? Okay. All right. Then let's go to the next page. If this is true, then what do the x components of T3 and T5 have to equal? They have to equal 0. And what are the y components? That's right, Christopher. And what do the y components of T3 and T5 have to equal? They have to equal 49. That's right. So T3 and T5, when you add that, you're going to have an I component and a J component. The I components are going to have to equal 0, add up to 0, and the J components are going to have to add up to 49. And that's how we get these two equations. Okay. So far, are we good here? Are we comfortable up to here? Once you have these two equations, you draw a good picture, you get two equations, and once you have those two equations, you're going to be okay. The goal is getting those two equations. Thank you, Ryan. Thank you, John. How do you know it's 49? Because, well, 49 you had 49J. So you had before, you had 0. If you go back to the previous page here, you have T3 plus T5 has to equal 0I plus 49J. So that means that T3 and T5, the sum of your I components has to equal 0. Has to equal 0I. And the sum of your J components, because remember, you're adding T3 and T5, that has to equal 49J. That has to equal 49J. And that's how we get these two equations. Does that clarify, Christian, for you? Does that clarify? All right, great, great. Now the book example will deal with the problem. Example 7 will deal with the problem where you have a weight that's 100 pounds. Well, pounds is already a unit of force, but in this problem, we had to get our unit of force by taking the mass of the weight and multiplying it by acceleration due to gravity, which is 9.8 meters per second squared. And that's how you got 49. You use 9.8. Don't use 9.82 though. Use 9.8. But all right, so now we got two equations and two unknowns. So based on the first equation, the magnitude of the tension 5 vector would be equal to the magnitude of the tension 3 vector times the cosine of 52 degrees over the cosine of 40 degrees. Okay, I'm going to do a substitution. I'm going to solve for the magnitude of T sub 5, and then I'm going to substitute that magnitude of T sub 5 in the second equation. Well, yeah, I understand. I understand, Eric, but we gotta work with it. So it turns out then that when I make this substitution, I end up with this equation, and I can factor the magnitude of T sub 3 out, and then I can divide both sides of this equation by this here. And I computed it. You have to have your calculator or Desmos in degree mode, 1.3046. And you got to go out a lot of decimal places because WebAssign is very picky about about decimal places and accuracy. Okay, so turns out that the magnitude of the tension vector T sub 3 then is going to be 37.56 newtons. Now in the instructions, always look in these word problems, look for the instructions. It might say round to the nearest tenths place, round to the nearest hundredths place. You want to make a habit of looking for that, because on the exam, if you have a problem where you get an answer and you don't round properly, the exam will count it wrong. And you don't want to miss problems because of that, right? So always read those instructions carefully. All right, are there any questions? Are there any questions down to here? Are we ready to go to the next page? All right, all right. Well, we'll go to the next page then. Now that we know what the magnitude of the T sub 3 tension vector is, we can now solve for T sub 5, the magnitude of the T sub 5 tension vector, because this here was the magnitude of T sub 3. I feel I'm pretty good with this mouse. A lot better. I mean, I'm getting a lot better with it. I mean, I'm good with it, but I still think I might get one of those styluses, just because, you know, I don't know. I've heard different stories. They can be hard to use, take time to get used to, but that's fine. Okay, so you get 30.19 newtons, and now you can substitute in your values for the magnitudes of the tension 3 and tension 5 vectors. Okay, here's where we substitute the magnitude of the tension 3 vector, and here's where we substitute the magnitude of the tension 5 vector. And then, based on that, you're able to find the actual vectors themselves. Absolutely fascinating problem. Do you think you might see this on your exam? Problem like this, or something similar, or something with tension vectors or force vectors? Yeah, of course. All right, very likely. All right, let me know if you have any questions. Take a moment to copy things down. Yes, Christopher, all the recordings of the lectures will get posted under course content in Blackboard. They will indeed get posted. Do not worry about that. Good question. Okay, are there any questions at all? Right. Okay. Well, if there are no, may I move on? Has everybody had a chance to copy okay? Well, that's nice to hear, Christopher. And you know, my expertise is in mathematical statistics. So some of you have had courses I've not had, but anytime I do things in math, and this is, of course, this is, an application to physics here. I always try to think simply, and hopefully things have been clarified here. Very good. Thank you, Eric, for that input. Very good. Very good. Eric says this is similar to Physics 1 and basic engineering courses. So, hey, I feel good. I know some, I know good things, and that's good. Absolutely. Setup is key. That's right, Christopher. Did I show you where the course content was in Blackboard? Did I remember to do that? Does anybody need to see that? I can do that real quick here. If you, hold on here, maybe I didn't have a chance to show that. I'll do it in the lesson, it's fine. If you go into Blackboard and look under course information, well, no, when you go into Blackboard, you're put right into course information. But if you look at course content, okay, course content, of course, we're in chapter 9. Just click here to see the course content. It should say in chapter 9, I'll correct that. Click here, and then here is section 9.1. Here, if you click on that link, that'll get you the recorded lecture for 9.1, and then 9.2, we have vectors from last class, and I'll be putting another lecture in. So absolutely, we will get the course content updated to include today's lectures. Not a problem. Okay. All right. Well, we're going to move on now to section 9.3. We're going to talk about the dot product. The dot product. And what I'm going to do is actually give you, well, no, I'm going to go right to, I think, right away to an example here. I'm going to go right to an example. So let me bring it up. I got to bring it up. Got to upload it. Just give it a moment here. Good, here we go. We're going to get right to an example. Let me stop the recording here because